Today we have problem 10, the last problem from the Harvard MIT math tournament, and it's a pretty good problem, pretty cool one too. We're given that Jacob and Bojack each start in a cell in the same 8 by 8 grid, and possibly different cells, and they listen to a sequence of cardinal direction calls, right, north, south, east, or west. And when a direction is called out, Jacob always walks one cell in that direction, while Bojack walks one cell in the direction that is 90 degrees counterclockwise of the called direction. So if, for instance, east is called, then I guess Jacob will walk one cell east and Bojack will walk one cell north. Um, and if either person can't make a move without leaving the grid, so I guess they're on the edge, they just stay inside and don't do anything. And so over all possible starting positions and sequences of instructions, we want to find the maximum possible number of distinct ordered pairs, uh, I guess Jacob's position and Bojack's position, that they could have reached. Yeah. And so let's start out by, I guess, drawing out this problem first. We have an 8 by 8 grid. Eight by 8. And let's just put Jacob somewhere like here, and then Bojack somewhere like here. Then I guess marking each direction with like a different color, something like this. Jacob will follow each direction as called, but then for any move that Jacob makes, um, Bojack will make in the 90 degree counterclockwise direction. So if blue was called or east, Bojack would move north, and everything's just rotated by 90 degrees. Right, and so what's the hard part about this problem? I guess it's the fact that Bojack is moving in a different direction than Jacob every single time a direction is called, right? 90 degrees counterclockwise. So it'd be really nice if we could somehow change the problem in a way so that Bojack moves in the same direction as Jacob. Because surely that has to be easier than looking at them moving in two different directions every single time. And the idea behind doing that is, right, the direction that Bojack moves in is 90 degrees counterclockwise. So why not just rotate Bojack's entire, I guess, frame of reference sort of by 90 degrees clockwise again to undo that. And so what I mean by that is for any starting position that Bojack starts at, you rotate it around the center point of the grid 90 degrees clockwise. So if you do that, we'll call the position Bojack will be at, let's call B prime, will be mapped to here in this example. Um, and then looks ugly. And then while we're still rotating his entire frame of reference, that means his cardinal directions will also be rotated as well. So, right, if let's imagine Bojack was just initially facing north, then when you rotate him, his north will be this way now, or east. So all his sense of direction will also be rotated by 90 degrees, and in particular, it will now look like this. And now what we have is that B prime's, sense of movement is now in sync with Jacob's. And you can sort of convince yourself that even after this rotation from B to B prime, um, B and B prime still have the same set of legal moves, no matter any starting position and any direction that is called, right? Because, for instance, let's say two north directions were called. Let's say it's north-north. Then B would have to move one direction up here, but then one more north will take him out, so he just stays there. While B prime, or I guess this would be east. If two easts were called, then B would move two directions upwards, but just stay here, while B prime would actually move two directions east, but again, he's at the edge and can't move, so he'll also stay in this cell. And so, in terms of counting the number of distinct ordered pairs of Jacob's position and Bojack's position, right, we see that we have any ordered pair G or JB, let's say, will still immediately, it's like a one-to-one mapping to just any ordered pair J and B prime, because we had that B and B prime are moving in the same way. So any new position that B is in, there will be a corresponding new position that B prime is in. So now we can just look at, the number of distinct ordered pairs of Jacob's position and B prime's position. I'll just say J and B prime for now. And now, again, this is much easier to analyze because they are moving in sync. Let's say, any cardinal direction that's called, let's say south this time, they'll just move together. Right? And so now, how do we analyze this? You can sort of imagine, because they are moving in the same direction, you can try to, they're moving in the same direction, you can try to imagine sort of like a box bounding them. Right, so they're the corners of the rectangle of the box. That's of this, I guess, smallest rectangle that surrounds them. Then any move really sort of just moves the box. We can think of it as just moving the box instead. Right, so imagine, let's say east was called, right? Let's say west was called. So now Jacob is here, B prime is here. Then it's just essentially the rectangle. If we draw the rectangle for the new position, it just moved one spot to the left or westward. Um, and then how about if, I guess, yeah, given any two positions now, we can just think of it as the box surrounding them, and then each direction just moves the box somewhere in the grid. But what happens if the case when the box is on the edge, right? So let's say, let's get rid of this. I'll draw this one back in. Let's say they moved east this time, and we have J and B prime. So now their box is like this. And what happens if they move east again? Then we'd have to go here. J would go here, but B prime would stay the same, right? Because going east would take him off the grid. So instead, he just stays still. So now, after this case, our new box, the width of it shrunk by 1, right? Because J moved right by 1, but B prime stayed still. And so now, we can now just analyze, the height and width of a given box. And we can see that this quantity, the height plus the width, is decreasing, or it's non-increasing. right? Because every time we move the box, if both positions are able to move, then the entire box just shifts, so this quantity stays the same. And then if it's on the edge, then one of these quantities would decrease. So their sum also decreases by 1. And so this quantity is non-increasing. And given such a quantity, right, in this case we have 4 by 4 for the red box. What is the total number of distinct ordered pairs that J and B prime could have? Again, given a fixed sort of half perimeter of a rectangle. Well, if its height is h, then there are its height. If its height is h and the entire length of the box is 8, then there are just 9 minus h ways to move up and down, right? So for instance, since this is 4, we can either have 4 here, 4 here, 4 here, 4 here, or 4 this way. And that is 5 ways. So 9 minus 4 is equal to 5. And similarly, in the width direction, right, this is just also 9 minus w. So given a fixed h plus w quantity for a rectangle, the number of distinct positions it can be at is 9 minus h times 9 minus w. And this quantity is maximized when um, 9 minus h and 9 minus w are closest together. And that implies h and w are also close together. And so we have that to get h and w as close together, if h and w are if h plus w is even, and then we just have h is equal to w, that is the closest together they can get, while still having that both h and w are integers, right? And so in the other case, if h plus w is odd, then we can just say like h is equal to w plus 1. Or w is equal to h plus 1, but it should just be the same case. So how does this help us? Well, we have that this quantity is non-increasing, right? And the biggest it can be is, I guess, the entire rectangle this way, right? Just the entire box for the square. So that's 8 by 8. So you have that h plus w can equal anything from 16 to the smallest it could be would just be a 1 by 1 square, right? If j and b prime occupied the same square, right, height and width would both be 1. So this would just be 2. And so assuming that h plus w can take on somehow every single one of these values, then we can directly upper bound the total number of distinct ordered pairs by for each summing over for each value of h plus w the maximum value of this quantity. And so when h plus w is 16, then 9 plus h, or 9 minus h, times 9 minus w is maximized when h plus w is equal to, or h is equal to w is equal to 8. So this is 1 times 1. If h plus w is equal to 15, then 9 minus h times 9 minus w is maximized when h is equal to 7 and w is equal to 8. So this is 2 times 1. Or you can continue this. You see there's sort of a pattern of you just increase each one of these quantities by, or one of these quantities by 1 each time, and then increasing the other one. And so for instance, just as another example, when h plus w is equal to like 7, then 9 minus h times 9 minus w is maximized when h is equal to 3 and w is equal to 4. So you have that this quantity is equal to 6, or 8. W is equal to 4. So this is 6 times 5. And this will continue on until you get to 7, or 7 times 7, 8 times 7, and then 8 times 8. And so how do you sum all of this up? Well, we see we'll have 1 squared, 2 squared, 3 squared, all the way till 7 squared, 8 squared. And then we can make all these terms that aren't the same also square by sort of taking out one factor from the bigger number. So we could write this as 1 times, or 1 plus 1 squared. 3 times 2 would be 2 plus 2 squared. And then we'd have 3 plus 3 squared. This will continue until 7 plus 7 squared. And so summing in this way, we have this sum of squares is 8 times 9 times 17 over 6 using the sum of squares formula. And similarly over here, we have the sum from 1 to 7 is just 7 times 8 over 2. And the sum from 1 squared to 7 squared is 7 times 8 times 15 over 6. And so adding this up, you get an upper bound of 372. And because of the structure that, we're only decreasing one number by 1 every time we decrease h plus w, we can actually reason that this upper bound is achievable by starting with an 8 by 8 square. Right, in this case, I'll copy this over. We can start with an 8 by 8 square, right? So we get 1 times 1, then move in any direction to turn it into an 8 by 7 square. Then we can achieve all of the 2 times 1 distinct positions here by just moving it left and right. And now we can move upwards, or in the north direction, to reduce the square to now 6 by 6. And then there should be 4 positions here, which we can get by just going down and then right and then up. And then we can just keep doing this, right? Decreasing one one side by one, and then just moving, you can sort of zigzag the rectangle through the entire grid to reach the maximum number of positions. And so this 372 upper bound is achievable and ends up being our answer.